Okay, let's unpack this. Imagine you've got these incredibly powerful AI models, right? The big
Yeah.
foundation models, the large language models everyone's talking about.
Yeah, the ones that can do seemingly almost anything.
Exactly. They can do so much. But maybe you need one to do something really specific, like generate code in a particular style, or answer questions only from a certain document, maybe.
Or even just adopt a very specific writing voice for marketing copy, that kind of thing.
Right. And getting them to do that usually means adapting the model somehow.
Which traditionally is, well, it's often a major hurdle, a real bottleneck.
It can be expensive, takes ages, needs tons of specific data, and you need, serious technical know-how to tweak it for every single new task.
It really limits how easily people can tailor these powerful tools.
But what if? What if you didn't have to do all that? What if you could adapt one of these huge models pretty much instantly just by, well, telling it what you want it to do
Yeah.
in plain English?
That sounds ambitious, skipping all that training.
Well, we've been diving into a paper that introduces something called Text-to-LoRA, or T2L, and it proposes exactly that kind of idea.
Text-to-LoRA. Okay, I'm intrigued.
So this deep dive is all about figuring out how this T2L technology actually works, what it can realistically do, and why it might just be a really significant step, a step towards making powerful AI specialization much, much more accessible for everyone.
Right, so the fundamental challenge here, as you sort of touched on, is taking these big general-purpose models and making them really good, really effective at a specific, narrow task. They're versatile, sure, but versatile isn't the same as highly specialized.
And the usual way to specialize, full fine-tuning,
Yeah.
well, it's just not practical for most people or most situations, is it?
Exactly. You're essentially retraining a massive chunk of the model, billions of parameters that needs enormous computing power, huge task-specific data sets, and it just takes a long time.
Which is why techniques like parameter-efficient fine-tuning or PEFT came along, things like LoRA. That's a really popular one.
LoRA, Low-Rank Adaptation.
Ah.
Yeah, that was a big step because you don't have to mess with the original model weights, right? You just kind of bolt on these smaller adapter matrices and train those.
Precisely. LoRA freezes the huge base model and only learns these small, low-rank matrices, usually called A and B, for specific bits of the network, like the attention layers. It massively cuts down the number of parameters you need to train.
Definitely more manageable. But, and I guess this is the crucial point for this T2L paper, even with LoRA, you still need a specific data set for each task, right?
Yeah, you still have to run a training job for every new task.
Right.
You still have to fiddle with hyperparameters to get it right. It's still an engineering effort every single time you want the model to do something new.
Okay, so LoRA improved things, definitely made it more efficient, but it didn't completely get rid of that manual task-by-task training requirement.
Exactly. And that's the problem. Text-to-LoRA, T2L, is trying to crack with this instant adaptation idea.
Yes, that seems to be the leap they're aiming for. T2L isn't really a method for fine-tuning the base model itself, and it's not even training a LoRA adapter on task data in the usual way. T2L is, well, it's something else. It's a model that creates models.
Hang on. A model that creates models.
Yeah, specifically, it's a type of neural network called a hypernetwork, and its whole job is to generate those LoRA adapter weights on demand.
Wait, so instead of me training an adapter for, say, summarizing legal documents, I use this T2L model, and it just makes the adapter for me.
Exactly. That's the core idea. And the really clever bit, potentially, is that it generates these task-specific LoRA weights on the fly based only on a natural language description of the task you want.
So I just type in summarize legal documents focusing on liability clauses.
That's the concept. You just tell it what you need in simple terms.
And it builds the exact little LoRA tool needed for that job right then and there.
That's the goal. The purported magic is that it can generate these necessary adapter weights in, supposedly, a single inexpensive forward pass through this T2L hypernetwork.
Wow. Okay, so you completely bypass the whole traditional fine-tuning loop, even the standard LoRA training, at least at inference time. You just generate the adapter and slap it onto the base model.
Survey and apply. Yeah, that's the promise.
Okay, conceptually, that's fascinating. But how does this hypernetwork, this T2L thing, actually figure out what LoRA weights to generate just from some text? What does it actually take as input?
Right. So under the hood, T2L needs a few things. The most critical input is, as you said, a representation of your natural language task description. So the text you provide gets converted into a numerical vector, an embedding.
Okay, the task embedding. Makes sense.
But it also needs to know where in the base LLM this LoRa adapter is supposed to go, right?
Yeah.
Because LoRa modifies specific
Oh,
parts.
right. Like which layer, which part of the attention mechanism.
Exactly. So it also takes embeddings that identify the specific module within the base LLM, like, say, the query projection matrix in the attention block, and also the layer number, the layer index.
So it knows, okay, the user wants an adapter for the query projection in layer 10, and the task is described by this embedding vector.
Precisely. Based on those inputs, the task embedding, the module embedding, the layer embedding, the T2L hypernetwork, then outputs the actual A and B matrices, those low-rank matrices that form the LoRa adapter for that specific location and task.
And the paper looked at different versions of this T2L network.
Yeah, they mentioned different architectures, L, M, S large, medium, small, presumably varying in size and complexity, but they all share that same fundamental goal: map descriptions and locations to LoRa weights.
Okay, that makes sense structurally. But then how do you actually train this T2L model? How do you teach it to generate good, useful adapters? The paper mentions two different ways they tried.
Right, two main training strategies. The first one they call reconstruction. The idea here is actually pretty straightforward. You train the T2L hypernetwork to simply replicate or reconstruct the weights of existing LoRa adapters that you've already trained for specific tasks beforehand.
Okay, so you gather a bunch of LoRAs you've already made the old-fashioned way for various tasks.
Exactly. And you feed T2L the text description associated with one of those pre-trained LoRAs, and you train it to generate weights that are as close as possible numerically to the weights of that target LoRa you already have.
So it's like teaching it to be a really good mimic, learning to reproduce a library of existing tools based on their descriptions.
Pretty much. And a clear benefit they found here is that this approach can efficiently encode and kind of compress hundreds of those existing LoRAs into a single T2L model, which is neat.
And how well did the generated adapters perform?
Well, this is where they found something pretty surprising. T2L instances trained this way actually matched the performance of the original task-specific LoRAs on the benchmarks they were trained on.
Matched them. Okay, that's good.
But wait, it gets better. In some cases, like on the PIQA and WG benchmarks they tested, the T2L-generated adapter actually outperformed the original Oracle LoRa it was trying to mimic.
Hold on. The copy was better than the original. How does that even happen?
Yeah, it's counterintuitive. The paper suggests a hypothesis. Maybe the process of compressing those original LoRa weights into the T2L model, which is inherently a bit lossy, might act like a form of regularization.
Ah, like it smooths out some overfitting that might have been present in the original meticulously trained LoRa.
That's the idea, preventing it from being too perfectly tuned to the training data. However, despite that cool finding, this reconstruction method had a pretty significant drawback.
What was that?
It generally failed to generalize well to entirely unseen tasks. Tasks where it hadn't seen a corresponding pre-trained LoRa during its own training phase.
Okay, well, that makes a bit more sense. It learned to copy specific existing tools very well, but it didn't necessarily learn the underlying principle of how to build a new tool for a new job description.
Exactly. It learned the specific input-output mappings for the adapters it saw, but not the general relationship between task semantics and optimal adapter parameters.
So what was the second training method? The one that did manage to generalize?
That would be Supervised Fine-Tuning, SFT. This approach is quite different. Here, they trained T2L end-to-end directly on a diverse set of downstream tasks.
Okay, so not trying to copy existing weights anymore.
Nope. Instead, the training signal, the feedback for adjusting the T2L hypernetwork's weights, came directly from the performance of the base LLM when using the adapter generated by T2L on those training tasks.
Ah, I see. So it's not learning to match weights. It's learning to generate weights that actually make the base model perform well on the described task. The reward is task success, not weight similarity.
Precisely. And this, according to the paper, is where they found the real breakthrough. This SFT method enabled zero-shot generalization to completely unseen tasks.
Zero-shot generalization, that's the key phrase, isn't it?
Absolutely. It means T2L learned to map a novel task description to a useful set of adapter weights, even if it had never encountered that specific task or seen what its ideal adapter should look like during its training.
That's the magic trick, then. Being able to create an adapter for a task it wasn't explicitly trained for. Why did SFT work for generalization when reconstruction didn't?
The paper offers some analysis, including visualizations, to support their reasoning. They suggest that SFT implicitly learns to cluster tasks based on the kind of adaptation the base model actually needs to perform well. It learns the functional relationship.
Whereas reconstruction just focused on the weights themselves.
Right. And the problem there, they argue, is that LoRa-Bodger adapters for tasks that seem semantically similar might not actually be numerically close to each other in the parameter space. So just copying weights doesn't capture that deeper functional connection. SFT learns the mapping from description to effect, not just description to existing parameter values.
Okay, that makes intuitive sense. So when they put this SFT-trained T2L to the test in experiments, how did it actually do on those unseen tasks?
The results they report are quite compelling. The LoRAs generated by SFT-trained T2L successfully improved the base model's performance across a range of unseen benchmark tasks. They list things like RC, GSM8K, HeliSwag, OpenBookQA, PQA, Winogran, and others.
And how did it compare to other ways of adapting?
It consistently did better than baselines, like using a single generic multitask LoRA trained on everything, or just prepending the task description as part of the prompt to the base model.
Did the T2L-generated adapters manage to match the performance of an oracle, LoRa one specifically trained on that unseen task's data?
Not always perfectly closing the gap to those Oracle task-specific LoRAs, which, had the advantage of direct, extensive training on that specific benchmark dataset.
Right, the oracle had the best possible preparation for that one test.
Exactly. But the T2L adapters often got surprisingly close. And interestingly, echoing the reconstruction finding, they sometimes did outperform the Oracle LoRAs even on these unseen tasks.
Wow, even on unseen tasks. Again, maybe that regularization effect preventing the oracle from overfitting.
That seems to be the recurring hypothesis, yeah. That the generated adapter might be somehow more robust or generalized, even if slightly less perfectly optimized for that single benchmark instance.
Okay, performance is one thing, but you mentioned earlier it was supposed to be inexpensive.
Yeah.
How much more efficient is using T2L compared to, say, prompting techniques?
They included an ad hoc FLOPs analysis that's floating point operations, a measure of computation. Their estimate showed that using T2L for adaptation was significantly more efficient. They calculated a greater than 4x reduction in FLOPs compared to using three-shot in-context learning, ICL, with the base model.
More than 4 times cheaper computationally.
That's what their analysis suggests. So basically, generating the adapter with T2L is much faster and cheaper at inference time than trying to adapt the model just by giving it a few examples in the prompt.
That's a huge practical advantage, especially if you need to adapt models frequently or on the fly. And does this T2L approach work with different underlying language models?
Yes, they showed results demonstrating it works across different LLM families. They tested it successfully with Mistral, Llama, and Gemma models.
So the concept seems portable, not tied to just one specific architecture.
Which is good news for broader applicability, definitely.
Okay, let's dig into some of the other analyses they did. What happens if you train T2L on more tasks during that SFT phase? Does it get better?
Generally, yes. The experiments indicated a positive trend there. As they increased the number of distinct tasks used to train T2L via SFT, its ability to generalize and perform well on unseen tasks tended to improve.
Especially if they scaled up the compute power for training too.
Right, particularly when the training compute scaled proportionally. This suggests there's positive transfer happening. Learning how to generate adapters for a wider variety of tasks actually helps it become better at generating adapters for new, previously unseen tasks. It learns more general principles of adaptation.
Okay, that makes sense. Now, what about those natural language task descriptions you feed into T2L? How sensitive is it to the exact wording?
Oh, hugely sensitive. This was a key point in their ablation studies. The quality and the alignment of the task description are absolutely critical.
Alignment meaning, does the description actually match what the task data requires?
Exactly. If you give it a clear, accurate description that truly reflects the task you want the adapter for, you tend to get a good adapter and strong performance from the base model.
And if the description is bad, or just random text?
Performance degrades significantly. If the description is unaligned or just noise, the generated adapter doesn't help, or might even hurt performance. It really relies on understanding the instruction.
But they also found something interesting about different good descriptions, right? about steerability.
Yes, they had this neat qualitative example. I think it was figure 4 in the paper. It showed that providing different but still aligned and accurate descriptions for the same underlying task could steer the base LLM to produce the correct answer, but via different reasoning paths or explanations.
So how you phrase the request, even if accurately, can influence how the AI behaves, not just whether it succeeds. It gives the user some creative control.
That seems to be the implication, yeah. It offers a way to guide the style or focus of the model's response through the description used to generate the adapter.
And what about internally? Did they look at whether T2L was actually generating meaningfully different adapters for different tasks?
They did. That visualization analysis we mentioned earlier, figure 5, supported this. It showed that the internal activations within the SFT-trained T2L model and also the characteristics of the LoRA matrices it generated tended to cluster semantically based on the task type.
So adapters for similar tasks looked similar internally, while adapters for different tasks looked distinct.
That's the idea. It provides evidence that the model isn't just spitting out random weights. It's learning task-specific representations and dynamically generating genuinely distinct appropriate adapters based on the text input.
Okay, stepping back then. What's the big picture here? What's the potential overall impact of this text-to-LoRA concept if it continues to develop?
Well, I think the most significant potential impact, as the paper highlights, is really about democratizing LLM specialization. It massively lowers the barriers.
Because you don't need the huge data set or the complex training pipeline for every single adaptation anymore.
Exactly. If this works reliably, you could potentially adapt a powerful model for countless specific needs just by describing what you want it to do. It makes customization much faster, near instantaneous at inference time, and requires less specialized expertise and fewer computational resources compared to traditional fine-tuning or even standard LoRA training.
That really could open up LLM adaptation to many more people and applications. But it sounds like it's not quite a magic wand for everything just yet. There are still limitations.
Oh, for sure. It's definitely not a silver bullet at this stage. The paper is quite clear about the current limitations.
Like the reliance on the task description being good.
Yes, that's a big one. It hinges on having high-quality, well-aligned task descriptions. Garbage in, garbage adapter out, essentially.
And what about the types of tasks it can generalize to?
While the zero-shot generalization they showed is promising, its ability to handle tasks that are fundamentally different from the kinds of tasks it saw during its SFT training phase, well, that needs more exploration.
Right. If it was trained mostly on, say, text generation and Q&A tasks, could it generate a useful adapter for something wildly different, like controlling a robot or analyzing protein folding, just from a description? Maybe not without seeing similar types of tasks during training.
That's a fair question. The generalization might be limited by the diversity of the training task distribution. Also, while the generated LoRAs are often effective, the paper acknowledges they might not yet consistently reach the absolute peak performance you could get from a meticulously hand-tuned, task-specific adapter, especially for really complex or highly specialized domains.
So there might still be a gap for those highest stakes applications where every last drop of performance matters.
Potentially, yes. And finally, they point out that their work focused specifically on generating LoRA adapters. There might be other ways to parameter efficiently modulate LLMs that could be targeted by a similar text-to-adapter approach in the future, perhaps even more effectively.
Okay, so wrapping this up, what does this all mean? Text-to-LoRA seems like a really fascinating step, doesn't it? Towards a future where maybe customizing one of these incredibly powerful AI models for your very specific need could be almost as simple as typing out a sentence describing what you want.
It definitely points in that direction. It significantly lowers those technical and computational barriers that have traditionally made specialization hard, enabling adaptation that feels almost instant compared to the days or weeks fine-tuning could take. That's a big shift.
This ability to generate specialized AI capabilities from just a text prompt. It feels a bit like having a kind of universal translator, but for AI tasks instead of languages.
That's a nice analogy. It translates human intent, expressed in language, directly into model configuration.
But it also really brings up an important point, doesn't it? As models like T2L get better and better at interpreting our natural language instructions to shape AI behavior, how much more critical does the clarity, the precision, the quality of our communication become to make absolutely sure the AI does exactly what we actually intend it to do?
That's a profound question. The power shifts towards the instruction itself. the responsibility for specifying the task correctly and unambiguously grows significantly. It puts the onus on the user's ability to communicate effectively with the machine.
Definitely something for all of us to think about.